Hello, welcome to our first carboxylic acid video. In this video, we'll introduce the carboxylic acids, and precisely we'll be talking about the alkanoic acids, which are the saturated ones. Of course, we have the alkenoic and the alkynoic acids, which are unsaturated forms of the carboxylic acids. But like I said, our focus will be on the saturated ones, also called the alkanoic acids. Carboxylic acids are compounds of general formula RCOOH, where the COOH there is the functional group, and that functional group is called carboxyl. The COOH group is actually two functional groups in one. So there's the CO group that is called carbonyl, and then there's the OH group that is called hydroxyl. So that if we put these two together, we have what is called carboxyl. So carboxyl is COOH, and that's the functional group in the carboxylic acids. Now for the carboxylic acids, COOH as functional group, we say the COOH group is polar, and we'll say a word about it later under characteristics. But for now, the first member of that homologous series is HCOOH. It has only one carbon atom, and its name is methanoic acid. Meth for one carbon. And that methanoic acid is also called formic acid. Why is it called formic acid? Because in the times past, it was obtained from formica. Formica is Latin. In English, that is ant. So Latin formica. Formica in Latin is ant in English. So in times past, it was obtained from ants by crushing ants, or even some plants called nettles. So as a result, it got the name formic acid. So formic acid is methanoic acid, and that compound we'll talk about much later, although in recent times it's no longer obtained from ants, but from a simple chemical reaction. Now for the second member, which is apparently the most important member, its name or its formula first is CH3COOH, and its name is ethanoic acid. This ethanoic acid is also called acetic acid. So acetic acid is ethanoic acid, and it is the acid that is found in vinegar. What is vinegar? Vinegar is sour wine. So palm wine that has stood for a long time is called sour wine or vinegar, and in that vinegar there is plenty of ethanoic acid. So we say ethanoic acid is the second member of the series, and is obtained from a natural source, which is vinegar. There are various other carboxylic acids that come from natural sources like that. For example, rancid butter is known to contain the fourth member, which we call butyric acid. So we have several other alkanoic acids: citric acid, malonic, fumaric. In fact, most of the acids that we find in living systems are carboxylic acids. Leaving that story, the next thing here is types of carboxylic acids. Depending on the number of COOH groups that we have present, carboxylic acids may be classified as monocarboxylic, dicarboxylic, or polycarboxylic. So that if we look at this formula, I'll repeat it here, CH3COOH, it's the formula of an alkanoic acid. And in that alkanoic acid, we have how many COOH groups present? One. So we say it's a monocarboxylic acid. Monocarboxylic acid. And for monocarboxylic acids, usually the basicity, which is number of replaceable hydrogen, is usually 1, and it is that hydrogen in the COOH that's the replaceable one. All of these other hydrogens, for example, cannot be replaced. Then see this one, COOH bonded to COOH. This is called ethane dioic acid. This ethane dioic acid is also called oxalic acid. So oxalic acid is ethane dioic acid. I'll put the other name there, ethane dioic acid. So it's a dicarboxylic acid. Dicarboxylic in the sense that it contains two COOH groups. Sometimes we don't write this acid like this. We write it as H2C2O4. So whether you see it written as H2C2O4 or written in the structural form like this, or even written in a condensed form as COOH bracket 2, it remains oxalic acid. It remains an example of dicarboxylic acids, and its basicity remains 2. Then there's a third case. We call them the polycarboxylic acids. Polycarboxylic, those ones have more than 2 COOH groups. So we can have 3 COOH groups, we can have 4, and so on. But look at this very good example of polycarboxylic acids. We have COOH, COOH, and COOH. Then on this side I have CH2. Going up I have C bonded to that with OH, and then again I have CH2. This compound is called 2-hydroxy propane 1,2,3 tricarboxylic acid. 2-hydroxypropane 1,2,3 tricarboxylic acid. Its trivial name is citric acid. So this is citric acid that is very much abundant in lime and lemon, as well as some other citrus fruits. So citric acid is called 2-hydroxypropane 1,2,3 tricarboxylic acid. So it's an example of the polycarboxylic acids because its COH groups are already more than 2. Actually, we have 3 of them. Now, sometimes when we have monocarboxylic and dicarboxylic, we could go ahead to speak of tricarboxylic before polycarboxylic. So in that case, you may now need to include examples of carboxylic acids that have up to 4 COOH groups. They are not very common, but yes, we have examples such as the substance called EDTA, ethylene diamine tetraacetic acid, an anticoagulant. So we'll leave that. Moving on, we talk about the characteristics now of alkanoic acids. Alkanoic acids show solubility in water. That's the first characteristic I would like to mention. They are soluble in water, and as their molecular weight increases, their solubility drops. It means therefore that moving from ethanoic to propanoic to butanoic, pentanoic, and so on, solubility generally decreases, such that for a substance like benzoic acid, we say its large molecular weight does not allow it to dissolve properly in water. So their solubility is fair, but as it increases, as their molecular weight increases, as we go from low members to high members, we discover that their solubility decreases. Now, apart from that, in terms of boiling points and melting points, they have higher boiling points and melting points than alkanols. But why is that so? You may need to listen to this. Alkanols have higher boiling and melting points than alkanes, alkenes, alkynes. Hydrocarbons of equal number of carbons. So think of ethane and ethanol, 2 carbons each. But the boiling point of ethanol is far higher than that of ethane. The reason would be that ethanol forms hydrogen bonds, but ethane does not. But what about ethanoic acid and ethanol? Ethanoic acid has a way higher boiling point than ethanol. The reason would not be that ethanoic acid contains hydrogen bonds, because ethanol also contains hydrogen bonds. Instead, ethanoic acid contains more hydrogen bonds such that it undergoes or it exhibits what we call dimerisation. So dimerisation is the reason alkanoic acids usually have higher boiling and melting points than their corresponding alcohols. Now this is what we call dimerisation. We have R, C, O, O, H. That's the general formula for an alkanoic acid. I'll repeat that formula on the right. So I have H, O, C, double bond O, then R. So I've written the alkanoic acid formula twice, and then I'm going to connect these two formulas by hydrogen bonds like this, 1 and then 2. So it is said that between two alkanoic acid molecules, there are two hydrogen bonds, unlike between two alcohol molecules, which we have as H, O, R, H, O, R. So between two alcohol molecules, we have just one hydrogen bond. So we say that alkanoic acids exist as dimers. They have two hydrogen bonds between two molecules of alkanoic acid. So those things will increase the boiling and melting points of the alkanoic acids relative to the alkanols that are corresponding to them. So they show dimerisation, which leads to high boiling points and melting points. That's another characteristic of the alkanoic acids. Then, of course, as acids, there are certain characteristics we expect of them. For example, we expect that they'll turn blue litmus red. We expect that they'll react with the metals, the very reactive metals, to give off hydrogen. Then we expect too that they will react with trioxocarbonates to give off that colorless and odorless gas that turns lime water milky. Yeah, that's CO2. Now, having said those, I would like to look at their acidic strength. As a matter of fact, among organic compounds, the carboxylic acids are the most acidic. There are various organic compounds that could show some degree of acidity, such as the phenols, but none of them shows the degree of acidity that the alkanoic acids show. So they remain the gold standard when it comes to acidity. Now see this. Let's say I write a carboxylic acid as R, C, or let's say CH2, then C, O, O, and H. That's a carboxylic acid. We don't know its name because my R is not defined. Now this carboxylic acid, generally carboxylic acids are weak acids, we agree. But as an acid, as a Bronsted acid, if you remember the Bronsted and Lowry theory of acids and bases, as an acid, this substance should be able to give off this replaceable hydrogen. And depending on how well it does so, it may be called a strong acid or a weak acid. What we mean is, if this hydrogen leaves very easily, then this acid will be regarded as strong. But if this hydrogen is reluctant to leave or finds it difficult to leave, then this acid will be described as weak. Now in this case, as this substance is now, there is a certain ease that this hydrogen has when it comes to leaving. We don't know about that ease for now, but we can compare it against another structure. So look at this structure that closely resembles that one. So we have everything intact, just that right now one of the hydrogens here has been replaced by fluorine. What will be the impact of this fluorine? I'll tell us shortly. But back to this. Between this oxygen and the hydrogen, there is unequal sharing of the pair of electrons here. And that unequal sharing leaves this oxygen with a partial negative charge and the hydrogen with a partial positive charge. Now, what I'm about to say next is not exactly true, but would be very useful for explanation purposes. What I have to say here is the bond between the oxygen and hydrogen, this line we're looking at, actually was formed by oxygen bringing one electron and hydrogen donating one electron as well. So they both donated one electron each, and then the two electrons that they contributed here are not being equally shared. Oxygen, being more electronegative, is taking more than half the share. So you can assume that they are sharing the pair of electrons here at, let's say, 70-30. That's the ratio, the sharing formula, 70-30. So oxygen is getting more than half the share. Hydrogen doesn't like that. So if oxygen could normalize this a bit, maybe 60-40, hydrogen could consider. But imagine that this sharing becomes worse, maybe becomes 90-10, then the hydrogen may become so disadvantaged that it falls off. It will be like two people being on a bed. Here's a bed, then you have one person, another person. Actually, this bed can take two people. But what if this other person becomes so big and this is a sleeping position now? See this person. It means that the second person here may begin to manage, and if this worsens, that person could fall off. So it's something similar that's happening here. Now, I have introduced fluorine at this position. How does that affect this 70-30 relationship? Fluorine is known to be an electron withdrawing group. So by inductive effects, fluorine withdraws electrons from this carbon. Remember that hydrogen is up there in reality. So fluorine will withdraw from this carbon. That effect will be transmitted by way of this carbon withdrawing electrons from that carbon. That carbon will in turn withdraw electrons from this oxygen, and then oxygen will withdraw electrons from the hydrogen. Now all that will lead to is a worsening of this situation. The electrons that hydrogen has already lost part of, it is going to lose more of. That means our 70-30 situation may just become 90-10, and that increases the chances of this hydrogen falling off. So it means that when I introduce fluorine at this point, the substance becomes more acidic than it was originally here. So this is a stronger acid than that one. But what if in place of F, I had introduced a group like NH2, the amino group? Unlike the F that is electron withdrawing, the amino group is electron releasing. So if that's what I had put here, excuse me, then there would have been donation of electrons from the amino group to the carbon, and from that carbon to this next carbon, and from that carbon to oxygen, so that eventually the situation here gets better. Imagine going from 70-30 to 60-40. That means that the hydrogen will be more willing to stay back, and the ease of that hydrogen leaving will be reduced, and that means acidic strength will also drop. So in summary, when you have an alkanoic acid like this, and you introduce an electron donating group to the alkanoic acid like NH2, then that will lead to a decrease in acidity or in acid strength. Whereas if you add an electron withdrawing group such as F, then that will increase acidity. And of course, take note that F and Cl, they are both electron withdrawing, but F is more electron withdrawing. That means bringing F here will increase acid strength more than bringing Cl there. Also, if you have a case like this one, R, CH2, 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 and COOH, acidity will be more greatly affected, more greatly increased if you put your F here than if you put it there, because in this case the F will have the inductive effect of the F will have to travel through a longer distance, and generally inductive effects die down or they die away with distance. So the further your F from the COH group, the lower its impact on level of acidity. So in fact, whether the group is electron donating or electron withdrawing, if it is too far from the COH, its effect will just die away. But when it is very close, then it has a stronger impact on the COOH group. That's a word on their strength, and if you ask me, I think we've said enough for carboxylic acids in this first video. Now there will be a second carboxylic acid video where I'll talk about how they can be prepared. So you look out for that second video for preparation of carboxylic acids. But in the meantime, you do well to subscribe to the channel, to tell your friends about it by sharing, by liking. Tell them about this channel, let them know what's happening here, and let them be part of it. Don't let the train leave them behind, as it were. Thanks for watching this video. I'll see you in the next carboxylic acid video.